I'm going to talk about assessment of running gears regarding rolling contact fatigue of wheels and rails based on stochastic simulations. This work comes out from a collaboration between KTH, ACT, Tribology Competence Center in Austria, and Virtual Vehicle, and the work has been carried out in Shift to Rail project Freightwell. We also had a collaboration with Tatra Wagonka, a freight wagon producer. I also want to mention my co-authors, Tomislav, Mihalj from ACT, Gerald, Trummer, and Christof, Marte from Virtual Vehicle, Visakh, Krishna, Saeed, Hossein, and Sebastian Stichel from KTH in Sweden. Short outline about the contents of my presentation. I will start with an introduction, then I will present the methodology we have developed, some results from the application of this methodology to freight wagons, and I will close my presentation with a short summary. To the introduction, the work is about wheel-rail tribology, which is a complex interaction between friction, wear, damage, as you know. And the question is, how is this wheel-rail tribology influenced? What are the influencing factors? There are many of them. It's the vehicle properties, of course. It's the operation of the vehicles. It's the track system, and also environmental, climate conditions, friction management. There's a big influence, of course, on the friction. So very complex overall problem. And the focus of this work is now what is the relationship between certain vehicle parameters, vehicle properties, and wear on wheel and rail, as well as on rolling contact fatigue issues, also on wheel and rail. And we want to take into account the railway operation in as realistic as possible way, and taking into account also some stochastics from this railway operation. Short, one slide about the state of the art when we talk about assessment of running gears with respect to wheel, rail, wear, and RCF. Many researchers use quite simple D-gamma-based approaches where they have a certain vehicle, one combination of wheel-rail profiles, one speed, certain addition conditions, and then they do calculations, calculate the D-gamma values, and based on that values, they assess the running gear is good or bad with respect to these topics. Of course, there are more advanced ones. For example, when you look to the literature, many researchers do wheel profile evolution predictions. Then they consider very frequently rail profiles. Sometimes they consider stochastics of the railway operation. They do also some assessment of wheel RCF. But still, when you look to an overall assessment with respect to wheel and rail, wear and RCF, they do not account, for example, for the evolution of the wheel profiles and its impact on rail RCF. So our idea was to have a full integrated approach where we consider the development of the wheel profiles because this is influenced by the running gear technology itself and its impact on wheel and rail RCF. So let me come to the methodology. It's a, I think, very typical approach to predict wheel-rail profiles for a certain vehicle. So we define the scenario somewhere. We do multi-body dynamic simulations to calculate wheel-rail contact data, stresses, creepages, and so on. Then we do calculations with wheel-rail wear and RCF calculations. We do an update of the profiles, and then we go back to the multi-body dynamic simulations to, and then the loop is running again until we reach a certain distance. A bit more in detail about the scenario and the multi-body dynamic simulations. So here an example from a vehicle model. In this case, we use Genesis for doing the multi-body dynamic simulations. Regarding track, we have certain classes of rail curve radii. From the frictional side, we use distributions to get some stochastics into the system. They can be from measurements, from the tribometers, and so on. We also use distributions for the speeds of the vehicle. We use measured rail profiles dependent on the curve radius we are looking at. And we also used measured track irregularities. So the idea is to use, reproduce the operation of the vehicle as realistic as possible in the simulation tool. Then next I want to shortly present the used wheel well wear and RCF prediction models, and it's very important when we use this methodology, you get the full history of the wheel well profile contact data for every wear state of the wheel. So regarding wheel RCF and wear, we use the methodology developed by KTH. RCF, we calculate the shear stresses in the contact patch locally, compare it with the yield stress, and if it exceeded the yield stress, it is counted as it's considered in the RCF number. Some reduction of this RCF number is done dependent on the dissipated energy to account for the removal of cracks on the wheel surface. For wear, we use the hard model. I think it's very well known, and so we get the distribution over the wheel surface. Let me come to the rail RCF prediction model. This is, there we use the so-called wedge model, which has been developed at Virtual Vehicle. The main idea of this model is that the cracks always grow along this aligned microstructure on the rail surface because of these huge plastic deformations. So therefore, the model has a stress model, a plasticity model to approximate this plastic shear deformation in this surface near layer. We call it crack initiation layer. Then we have a fatigue model, and we also remove some of the damaged material from the surface. We distinguish three main cases. This is the first case with low loads, no preferred crack growth direction. This is a wear-only case. The second one is huge loads, where you have a very severe plastic deformed material layer on the rail surface, so you have a preferred crack growth direction, but they grow parallel to the surface, and they produce most of the cases wear only because they break off. And the third case is the interesting one with the wear and RCF case, where the cracks have again a preferred crack growth direction. They grow along the surface, they grow very fast away from the surface and cause macroscopic RCF cracks. So let me come now to the application of the methodology. We have compared two freight weighing running gears. It's the standard USC Y25 bogie, and we have called it the freight wheel bogie, where the main difference is that they have two cross bracings here to improve the steering properties. Freight wheel because it has been developed in the freight wheel project and shift to rail program by Tatra Wagonka. They were with some vehicle parameters. The red ones are the parameters we have varied during the work. Track, we investigated a Swedish track line, length of 500 kilometers between Luleå and Narvik. We have defined 9 classes of curve radii and added one with 200 meters to see also the difference of the two vehicles in a very tight curve. Results for the wheel. On the left-hand side, wear results. Comparison, the UIC bogie versus the freight wheel bogie. You can see a significant reduction of the wear for this certain track. Reduction also in the flange wear. On the right-hand side, you see the results for the RCF. I have to mention it's after 200 kilometer running distance, so the overall methodology is quite fast. We can really consider realistic running distances. And also here we can see two variants of freight wheel bogie, significantly reduced RCF numbers compared to the USC bogie, which can be seen by the color. Let me come to the rail RCF. Rail RCF, again, wear and RCF on the left-hand side, the wear results is the maximum depth of the wear for a certain case divided by the absolute maximum one. For the UIC bogie, high rail, low rail, and for the freight rail bogie here, dependent on the curve radii, and you can see that in all the cases the freight rail bogie shows significantly reduced wear values. It's a little bit different when you look at damage values. Again, here the same comparison. Most of the cases we have an improvement with respect to RCF, but there are two cases. For example, here in a 600-meter curve, the freight rail running gear has slightly higher damage values because it takes not into account only the stresses, but also the plastic shear deformation. So medium loads can result in damage, and the same is true here for tight curves, the low rail, where also the freight rail running gear shows slightly higher values. The nice thing from this methodology, you can plot the results over the rail surfaces, high rail, low rail, UIC bogie, freight rail bogie, and the boxes show where the freight rail bogie shows slightly higher damage values compared to the freight rail one. And you also see the distribution of the damage and so on. Okay, let me come to my last slide. 4 seconds for that. I have presented you a methodology. It's based on a wheel profile evolution prediction methodology. We think it's a quite nice approach. It's fully integrated because it takes into account the evolution of the wheel profiles, which are dependent on the rail running gear technology itself, on wheel, rail, wear, and RCF, taking into account realistic operating conditions, the stochastic nature, and we have applied it to this freight rail bogie versus UIC bogie, and this freight rail bogie shows significantly improved values compared to that one. So thank you very much, and I'm looking forward to your questions.